Hello everyone, today I'll be covering imports reconstruction of a Ryuk Ransomware sample. You can find some information about Ryuk malware family on Malpedia. Malpedia is also a good source of information about a wide range of malware families. I included the link to Malpedia below this video. If you want to download the Ryuk ransomware sample, you can download it from any run. I included the link to the run also below this video. For the imports reconstruction task, I will be using a tool called Scylla. Most of you are probably familiar with Scylla. It serves for imports reconstruction. It could handle 32-bit and 64-bit processes. It's available as a standalone solution, but also as a plugin solution for x64dbg. I will be using the plugin solution today, and the main reason why I choose to use Scylla is because many people have problem using Scylla. In some kind of situation, it doesn't work. And that's because people usually use the default options or default features. I will show you. When you use Scylla, you have options like using import stable Autosearch, and you can choose between normal search and advanced search. But it basically means that you are using the defaultly built-in features, and there are situations where this doesn't work. It basically find only the imports, it basically find only the importer stable, which is a part of import section in your original sample, which is basically what we don't need. We need the APIs function which are dynamically resolved during the runtime, and in these cases we can use a feature where we specify the memory range where the Scylla should operate on and the size of this memory range. It basically means that we have to get to the location where all dynamically resolved APIs addresses are already populated in somewhere in memory, and after we find this location, we have to fill in the start of the address of this location and the size of this memory range. After that, we push the button get imports, and Scylla will try to do its best to find all references and the import address table and use it for import reconstruction. Can go back here. So I hope that this video will also serve as a simple guide how one can use the Scylla not only with the defaultly built-in options for normal search and advanced search, but also for specifying the memory range where we already know where the import address table of dynamically resolved API function addresses is already populated. So let's jump to the IDA. After we put the Ryuk ransomware sample to IDA, we will land in a win-main function. You can see it here. If not, we can find this function where if you go to the start, and basically you are now in the entry point of the Ryuk ransomware sample, go ahead, and if you scroll to the end, usually the last function, which is returning some value, is the main function. So you can see it here. And now you are again on the win-main function. Now we can check the imports of this sample. We can see if we check the imports that there is already 117 imports, But what is interesting and why I'm suspecting that there should be some API resolving function which is executed during the runtime is because we can quite cheat on it, because we know that it's a ransomware sample and there should be used some encryption or decryption APIs for these routines. So we can try to find some crypt routine, and we cannot find anything like what is containing crypt, encrypt, decrypt, derive key or something like this. So now we are at the point where we could try to locate the API's resolving function. I usually start with two methods which are very often used in malware samples. One of the method is that the sample is using a very known combination of using load library function and get proc address. And the second one is commonly used in shellcodes, where shellcode is processing the process environment block structure, locating some module address or some module, and parsing the module structure, and locating the export table and finding the address of the some procedure. I will try to find the first method via the combination of load library and get proc address. So we can try to locate the get proc address. You can see it here. Try to find the references to this function, and we can see that it's very often referenced from the function on addresses at address 30006ODO and two times in memory from address 3005FFO. We can try to check the first function. Yeah, it's quite an interesting function, but it's surely not our API's resolving function. So go back and go again to the get proc address, references, and this is the most suspicious function, the sub 30006ODO. Go to this function, and if you check the start routine of this function, you can see that there are some XOR routines which are quite interesting, and it's more suspicious. After these routines, there are some switch cases. You can see it better from the disassembly view from the graph view. And here is the most interesting part. It's API's resolving block, which uses the combination of load library and get proc address. You can see it here. It's quite a big block. So how does it work? Basically, it works like it uses the load library function to get a handle to a library. The handle, it basically means that you are saving the base address of the library in some location, in memory location, and after that you are using this handle to the function get proc address, which you can see handle, and the second argument is name of your procedure or name of your API function which you want to locate. And after you locate this function in this module, you will save the get proc address is returning the address of this function, API function, to this memory address. This is quite interesting because these are locations where all the APIs will be saved. The API's addresses will be saved. So just check this, and you can see here quite plenty of the locations. It's in data section of the sample, and here is the start. We have to note this start and end of this memory range, because we will later specify it in the Scylla tool. You can see that there are not only the API's addresses, but also the handles of some modules. Be careful about that, and let's note it, because if you specify the memory range, this memory range, all this memory range to the Scylla tool, you will get some invalid tanks in Scylla. You will see it later, and that's caused because of the addresses, base addresses of modules, the modules handles. But it doesn't matter, because we can delete these invalid tanks and leave only the API's addresses. So let's note the start address. It's 3016 BCB8. Let's note it to some text file. API's start address. We will need the API's end address. Go back to IDA. Scroll a little down. You will find the location easily. Yeah, it's here. And ending 81, so the starting is here. This is the end of the memory range where all dynamically resolved APIs will be populated later. So let's note the end. And we can also note about APIs resolving function, and it's the function where we already are. It's the sub 300060do. Let's note it to the text file. Yeah, and we now have what we need, but there is one thing. The Scylla tool is not working with the end address of the memory range. It uses only the start address and size of this memory range, but we can easily calculate it with a little help of Python. If we subtract the start address from the end address, we will get the size of this memory range. So let's get the end address. Subtract start address. And you now know that the memory range is 356 bytes in size, but we have to convert it to hex, because Scylla is working with hex numbers, and 164. Let's copy that, and that's all what we need. Size. Now we know that the APIs will be resolved during the execution of this sample on addresses, start address here and end address here. It's in size 164 in hexadecimal. It's in size, and the API's resolving function is this. Now we have to try to find the fastest way how we can execute the API's resolving function in this sample, and navigate to this location, set a breakpoint after this location where we will have already all APIs resolved in memory, and after that we will use the Scylla tool. Let's jump back to the IDA, go back to the winMain function. Let's check the references of the API's resolving function. And we can see that the function is referenced 4 times from winMain function and 1 times from this start address. I don't know what it is. We can check. It looks like a start routine of some new thread. You can show the references. Yeah, it's a start address of some create remote thread. It doesn't matter now. We don't need this. We have to focus on the win-main function because it's the fastest way how we can get this function executed. So let's check the references and go to the closest one. Yeah, the function is here, and this is the start address. Yeah, this is the start of the win-main function. So let's check how we can get to this API resolving function the fastest way. We can check that this sample, this Ryuk sample, is getting the command line, and after it gets the command line, it uses the command line to get the arguments. It gets the arguments, and it checks. You can see here that if there is no error, it checks the count of arguments. If it's more than 2, it continues. If the arguments count is equal to 3, it continues, sleep 5 seconds, and there is another check. It's checking if the first argument is starting with the character 8. No, it checks if the second argument is starting with the character 8 and the third argument is starting with character L. Basically, it's a field of it's an array of arguments. Yeah, the first argument I forget to mention it, that the get command line arguments, it's returning something like array of arguments, and you have in this situation, in this where we want to meet these two conditions, we need 3 arguments, and the first command line argument is always our sample path. Yeah, so we are only interested in the second argument and the third argument. The second argument, as I already mentioned, must start with the character 8, and the third argument must start with the character L. What does it mean, the 8 and L? It's if you scroll a little down, you can see that the Ryuk Ransomware is expecting the 8 len as the argument. So we will put these 2 as a second and third argument, 8 len, and we will meet this condition 8L. And we will continue with executing our API's resolving function here. You can see it here, and this is the location where we have to what we have to find in x64dbg, and put a breakpoint there like that. And when we get to this location, all API's functions which are dynamically resolved during the runtime will be already populated in the memory range we already noticed in the text file. Oh. So this is the location which we have to find in x64dbg in our VM. So let's jump to the virtual machine and start our x64dbg and our Ryuk sample. Yeah, we will use the x32dbg because we are debugging the 32-bit sample. Well, we can use a recent file because I already used it, Ryuk sample, and we end on the system breakpoint. Yep, system breakpoint reached. First of all, be sure that in option and preferences you have enabled the entry point breakpoint. The system breakpoint, you can leave it, but be sure about the entry point breakpoint. And another what must be changed, go to the file and change command line. As I previously mentioned, there should be the path to the Ryuk sample. The second argument is 8, and the third argument is len, as we previously noted in IDA. Change this as a command line, click OK, and restart the debugging with this command line option. You will reach again the system breakpoint. Continue. You can check the breakpoint that there is the breakpoint on entry point. So continue, and you are on the entry point. Now it's the time to find the winMain function you already saw in IDA. So just go back to the IDA, scroll a little up on the winMain function, and you can see here the location, the address where the main function is located. Copy that, copy it to the VM, to the debugger. You can press Ctrl G and Ctrl V, paste. This is the address of main function. OK, and put a breakpoint there. Let's continue to the main function. We are here, and now we have to find the location where all the API's addresses are already resolved. So we have to find the API resolving function. We will use the graph view because it's quite a nice feature of x64DBG, and we can follow what we already did in IDA. So let's see. We can see it here that it's getting the command line. Now here is getting the command line arguments, and here is checking if there is some error. If there is no error, it's jumping here, and there is comparing if the arguments count is greater than 2, jump here, not jump here. So we already put as arguments 3 arguments, so the argument count is greater than 3. Here is the comparing if the arguments count is equal to 3. If not equal, jump here. If yes, jump here. Yeah, okay. We put 3 arguments, so we are here in this block, and here should be some comparing of the first character of second argument. Yeah, it's here, comparing if the second argument starting with 8, it's here. So if yes, jump here. If not, jump here. So our second argument is 8, so we will be continuing here. And here is the comparing if the third argument is starting with the character L. So it's here. If it's equal, it jumps here. If not, it jumps here. We supply the third argument as a line, so we will be here. And here you can see this is called to our API resolving function, and here is the address where we have to set our breakpoint, because our API's addresses will be already populated in memory. So we put a breakpoint here, set a breakpoint, and we can follow this the API's addresses, API's resolving function address, because I want to show you something. Yeah, we end it in the disassembly view. Follow the addresses. Yes. Now switch to the graph view because it could be better seen what I want to show you. It's our API's resolving function, and here we have the main block, which is using the load library and get proc address combination, and we can see that the location where the addresses will be saved is in the data section I previously noted, but it's here, so we can follow in dump. Okay, follow in disassembly, and now follow in dump, and this one. Yes, you can see that this address yeah 3016DCB8 is the API's start address, which will be populated later. So now you can see the start address and address here in the dump view, and we will go back to the main function where we put our breakpoint. Go to breakpoint, and here, yes, we can go to the graph view. Yes, and we are on our previously set breakpoints after the API's resolving function, where all APIs will be already resolved in memory. And we can press continue to reach our breakpoint, and also check the dump view. Yes, it gets populated with the dynamically resolved API's addresses. We already reached our breakpoint. We can make sure to check the EIP register. It's pointing to 3007ABE. It's our current location, and we got all the APIs already resolved. We can see all the addresses that they are really pointing to some API's functions. If you go to the addresses here, oh no, addresses, yep, go to the addresses and go to the function where we got, yes, here you can see all the APIs already resolved in memory. And you can also see that there is something what is not the API function. Here is something what is not the API function, and if you remember, it's handled to some module, and it's pointing to the base address of the module. There are quite a few, but it doesn't matter. It will be resolved as an invalid tank in a Scylla tool. You will see it later, and that's the reason why you will see the invalid tanks in the Scylla tool. And now we can use the Scylla plugins, Scylla. Yeah, we got the wrong entry point address, but we can fill the right one. If you go to the symbols, go to Ryuk sample, here is the entry point address, copy address, switch back, plugins, Scylla, and filled here the entry point address. Now you can see, if you want to try to use import address table Autosearch, as I previously mentioned, if you want to leverage the function normal search, click no and get imports, and you can see that we got only the function, this is the invalid tag, you can delete it, but these are functions which are already a part of import section of the original sample. So we are interested in with them also during the reconstruction, but the main point was to find the dynamically resolved API's function. So it was not helpful, but we can try to use clear it and try to use advanced import stable search advanced. So do you want to use the import stable search advanced results? Yes. And to get imports, basically you get the same. So it was not helpful with the Ryuk sample, but as I previously noted, we can leave this function because these are the function original located in the import section of the Ryuk sample. We need them too to be a part of the new import section in the dump what will be reconstructing thanks to Scylla. So leave these original APIs, and now is the time to find the APIs function which are dynamically resolved already and populated in memory. So let's back to the text file. We previously noted some main points. The start address of the memory range where our API is populated. Copy that, switch back to the VM. This is the start address, and the size is 164 in hex. So fill the size 164. Now get imports, and we have quite plenty of new imports, but what we can see here is also invalid tags. As I previously mentioned, the invalid tags are caused because in the memory range are also memory module handles, so the base addresses of some modules, and it's not a API function. So it's Scylla will show you it as invalid tag. Let's delete the invalid tags and leave the correct one. You can see now that we have 189 imports, no invalid. So let's dump the Ryuk sample from the process with the Scylla. Let's dump it and save it to some location. Well, we can save it to dumps. Save. And now it's time to press the fix dump, and with the fix dump we locate our dumped sample, what we previously did, and we will repair it with our located imports, and basically the Scylla will create a new section which is import section, and it will fill it with the information with these imports, these APIs functions. Fix dump, locate our previous dump. Open and import rebuild success. You can close the Scylla now. You can close the Ryuk, close the debugging, close the debugger, and now you have three samples: the original sample, the dump sample, and the repaired sample. We will use a tool called PEBEAR from Hasherazade with love. We will put the original sample and the already repaired sample. This is the original sample, and this is the repaired sample with the tool Scylla. Now you can see that in the original sample, in the imports, there is really the 117 imports we already saw in IDA, but in the new dumped Ryuk sample from memory, and you can see that in section is already the SCY section, which is created with the Scylla tool and filled with the imports, and you can see that there is also the 117 imports but unordered, and it's 189 imports. So we have the information about the original imports, and also with the information about the dynamically resolved APIs functions, all rebuilt in new import address table. We can close it and go to the IDA with this new sample, Ryuk dump SCY. So if you go to the, if you put this sample Ryuk dump SCY exe to the IDA, you again land in the winMain function. So let's check now the imports. You can see that we have 189 imports, and if you try to locate some imports which are part of encryption decryption routine crypt, and you can see now that there are plenty of crypt destroy key, crypt encrypt, crypt derived key, crypt import key, etc. And there is quite a, these are quite an interesting function for the encryption decryption routine. You can go back to the winMain function and check the API's resolving function. It's here. And check the addresses, scroll a little down, and you can see that the API's addresses are already resolved. And you can check the memory location, and you can see that the addresses are already populated and annotated with the proper type and name. What I quite don't like about this is that the new imports are not a part of the segment as like if you want to treat these imports as an external segment, you have to create new segment and make a class of this segment as an extern, and you will treat this imports as a segment as import segment, like IData. Yeah, you can check the Google for that. For example, IDA segment class name. And you can see that if you want to treat it as an extern definition segment, we have to specify the segment name extern. Okay, so back to the IDA. No, here. And because if you don't treat it as an external segment, you will be you will have the same color of the function as the function in code section. Yeah, it's quite bothering me. So if you navigate to the start address memory, the memory range of the dynamically resolved APIs, so it's here, and choose this memory range, select the memory range. It's quite here is quite tricky pink that you can select these all APIs, go to the edit segments and create segment. Create segments, call it as a, for example, new APIs. So one, you can check the start address, it's correct, and an address is Correct. Class name is extern, as we previously pointed in the IDA help. Yep, extern. And now press OK. And you can refresh the decompiler view, and it's better. But we can see that the original imports are also treated as some addresses as a code segment. We can navigate to the original imports and basically do the same as we did for the dynamic resolved API. So select the range. Yeah, we end here. Go to edit, segments, create segment, call it as a new APIs, for example 2, and check the style address and address is correct. Yep, it's correct. And class name extern. Okay, and now go to the main function to see the results, and you can see it here that it's already done. So if you you can see the color change, and we can treat it now as a import segment, so it's better. You can, for example, go again to the API resolving function, and if you scroll down, you can see that all these imports are treated as an import segment. So, for example, you can now compare crypt function which is using the crypt encrypt API. It's the most interesting one during the encryption routine. Yeah, we can see it here. It's this address, and for the comparing we can switch to the original not rebuilt with the Scylla tool sample Ryuk, and navigate to the function, this one, go here, and we can compare these results. So this is the repaired Ryuk sample with the Scylla tool, and this is the original sample. You can see the differences immediately. Yeah, we have all the dynamically resolved APIs function annotated, and with the proper type of this function. We can see all the arguments. We can see that no D words call or something like that. We can also see the original imports as before. And yep, that's probably all. You have all APIs which are dynamically resolved during the runtime rebuilt in new import section thanks to the Scylla tool, leveraging the feature as to specify the memory range where the Scylla should operate on. Well, that was about Ryuk and reconstructing of imports thanks to the Scylla tool. Thank you for watching, and I hope you enjoyed it.